Okay, welcome to Chapter 11. Chapter 11 is the last lecture we're going to get for the course. Hooray! Okay, now, previous chapter was all about describing these things in non-deterministic probability time, where there's practically no way to do them, at least not yet. We haven't figured out a technique for doing it. So, this is about how to do approximations for things like that. Okay, so the introduction starts on page 355. It talks about, NP problems exist, where there's not a regular P-style solution. Okay, we already got all that. And so we need to do some approximations. And how good are the approximations? Sometimes they're actually pretty decent, and sometimes they're not. There's actually a name for it. It's called Polynomial Time Approximation Scheme. Although I rarely ever hear that acronym, PTAS, but I'm just saying it exists. So let's just give an example of backtracking. So the traditional, I'm solving a maze kind of a problem. I hit a dead end in a maze, and I just basically need to backtrack to the last decision point that I made. So using recursion, or a stack, or a combination of the two, kind of makes sense, doesn't it? That way I can just rewind back to where I was, like hitting the rewind button. Okay, so that makes it easy to undo a choice and take another choice. So that's a depth first kind of approach. You're trying to go farthest you can, and then you back up and say, oh, that didn't work, right? So you're trying to go far. And then there's a branch and bound approach, which is kind of sort of similar, except for it basically takes the breadth first. It tries to get all the solutions that are nearest you first. So it uses a queue rather than a stack, in theory. But the technique is basically the same. I make my decisions, and I try to stay local, so to speak, before I start branching off. I make all the decisions about the immediate area first, and then make the next one cool. So the basic idea of a probabilistic algorithm is it's often better to guess the answer than to discover what the correct answer is. Let me give an example of the traveling salesman problem, where my job is to deliver trucks for UPS, and so I've got a list of addresses I need to go to, and I write up a nice little algorithm that finds the best the best route for me to travel and end up back at my station. So it's a complete loop and hits all the stations I'm supposed to go to in that day. Well, if the route comes out at midnight and I leave my truck at 6 o'clock, I only have 6 hours for this algorithm to work. And quite frankly, it's probably going to take, 20 hours for the solution to come up with the optimum. So I clearly cannot wait until I get to the perfect solution. I have no choice but to accept something less than perfect, because I just flat don't have the time to be able to get the perfect answer. So I'm okay with doing an approximation because I need it now, dang it, now. I can't wait. All right. So there's basically 4 different types of this type of approximation, so we're going to go through these. One is a numerical one. Okay, that's pretty straightforward. One's called Monte Carlo, and yes, we're talking about gambling. Las Vegas, and again, we're talking about gambling. And Sherwood, which is kind of weird, but it's kind of sort of like gambling. Okay, so those are the 4 types that we're going to be talking about. So on page 357, they start talking about greedy algorithms one more time. And if you remember the discussion way back in chapter 8 when we did the minimum spanning tree and the shortest path, those were greedy algorithms. Greedy meant that I don't wait until I get all of the data before I make my decision. I make my decision incrementally as I go. I look at the data and go, okay, I'm going to go this way. And then I look at the data and say, okay, now I'm going to go this way. So greedy means I don't have to wait. Well, clearly we're going to have to do that here in our approximations, because sometimes we can't wait 20 hours to get all of the data to figure it all out. That's not going to work. So almost all these guys are greedy algorithms where we just pick some number of increments. We say, okay, let's just do it 20 times and that'll be good enough. And after 20, then cool, we're done. And whatever answer you get is the answer you're going to get. It may not be perfect, but it's the amount that you can do in a fixed unit of work, whether that be time or loops or something. Okay, So one more time, minimum spanning tree and shortest path, those are greedy algorithms because they made decisions early without waiting for the data. Okay, good. So approximations for any of these NP problems, they don't really expect to get the optimal on the first try. That's probably not going to work. One way of doing it is, let's take like a random sampling of the data and do that. And then that'll do it, instead of using all of the data, I'll just take a random sample of something and then say, okay, I got it. That's one technique. And in that case, the size matters. I mean, if you take a 10% random sample, how good is your answer going to be? Kind of right. So the larger your sample size, the larger the most likely you're going to have getting the most optimal solution. Okay. So there's a goofy equation on page 358 that basically says if you're solving for a minimization problem, the value of the average of these guys over the value of the optimum, basically that'll tell you the size. This is not rocket science. It basically says if your sample size is big, you get good quality. If your sample size is low, you get low quality. I mean, that's basically all you need to get from this little diagram. Okay, so one more time, the traveling salesman approximation, page 358. Okay, one more time. We've talked about this before. Why won't minimum spanning tree work? Why can't I just use minimum spanning tree on this? Minimum spanning tree is going to visit all the nodes. Well, do I want to visit every single address in the entire city? Or do I only want to visit the addresses that are on my list to deliver packages to? So I don't want to visit them all. I definitely do not want to visit every single node. I want to visit only those places that have packages for today. Okay. What about shortest path? Couldn't I do a shortest path and then another shortest path and another shortest path? And then just keep going? Well, yeah, but that won't account for the return trip. And if you say, well, I have 100 places I need to visit, I'll do shortest path on the first one, and the next 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 one, next one, next one, next one, and then I'll do the shortest path back. That sounds like it might work. It doesn't. Not even close. Because the shortest path could get you way, way out on a branch, way far away. And then when it comes time for you to go to the next one, it is a huge travel to get to the next one because you're not looking at them as a whole. You're looking at them as individual spots, and that just don't work. Okay, so both MST and SP are not really appropriate here, mainly because I'm only going for a subset of nodes, not them all, and I want to have a return trip. Right? I can't just park my car or park my delivery truck. I need to get the delivery back to the starting point. Okay, cool. All right. So how it works. So here's a figure, figure 11.1. So an adjacency for a fully connected graph, blah, 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 blah. Okay, cool. So from 1 to 2. All right, so let's just go through this. Here's how I'm going to do this. I'm going to say there's 2 rules for how you select this thing. Do not form a cycle if you can. In other words, don't loop back on yourself. And then not on the third edge of an already considered node. Now that third edge sounds a little strange. All you have to do is just count. So just bear with me. So here we go. So I am going to pick the very first one is going to be 3, 5. Because see, that has a weight of 1. Cool. 3, 5. Got it. Then I'm going to get 5, 6 because that's the next one on the list. So you would think the third one would be 3, 6, but whoop. 3, 6 causes a cycle. 3, 6 gets me back to, so if I'm at 3 and 6, I have to basically throw that one out because it would form a cycle because I started it at 3. Okay? Okay? You following this? Okay, so I started with 3, 5 because it's the smallest one, and then I picked the next smallest one. I skipped 3, 6 because that would throw a cycle. And then I go to 4, 7. So 4, 7 is number 4. Okay, and then after that would be like 2, 7, which would be the 5. And then you think 1, 6, but oops, 1, 6 won't work because it's the third edge, because one of the edges is 3-5, the other one is 5-3. So I'm just counting up the number of times I hit 5. Okay, in either the x or the y, either the x or the y coordinate. So I already have a 3-5, and I already have a 5-6. So that would be the third edge. So I throw that guy out. So I skip 6 and go on to the next one. So those are the 2 rules. Don't create a loop, and don't get this third edge kind of a thing. All right, so how did we do if we did this thing by hand? Okay, we would end up with a total length of 53. Okay, now, this particular example, if done, perfectly, would end up with the optimal solution is actually 41. Okay, so we, using our technique, our approximation technique, took 53 units of measure. Let's just call them miles, okay? It took 53 miles, but the optimum is 41. So that's not all that great. Our approximation kind of sucks. I mean, we're off by about 30%. Are you willing to live with that? Maybe there's some tweaking we can do to keep going and process it a little bit further, or you just accept the fact that this is just not going to be one of those problems that we can solve in a normal amount of time. Okay. So let's just go through that thing one more time. This is designed to give us an approximation, and it just so happens, if you happen to know what the perfect solution is, how do you know that? Don't worry about it. I mean, someone told you, hey, the perfect solution is 41. Great, all right. And you came up with 53, well then that means you're just willing to accept the fact that using my technique, this is the best I can come up with. I mean, you could go through and say, well, let's substitute for that, then we'll substitute for this, we'll substitute for this, and just repeatedly substitute over and over and over until you come up with a better solution. You absolutely could, but that would probably take like forever to do that. Okay, so I'm going to move on. So I think we kind of beat that one. So bin packing. So bin packing is, this is kind of sort of like, you work as a bagger at a grocery store, okay? So things are coming down the conveyor, and I want to use the fewest number of bags as possible, because everything should fit in a bag, but it's like playing Tetris, right? And this one, I'll turn this one sideways and put it in the sack, and I'll take this one and put it in the sack. And these things are still coming off the assembly line. I can't let them pile up and go, wait, let me take this one out of this sack and put it over here and put this one in this sack. I mean, you could do a little bit of that, but the stuff is still coming off the assembly line, I mean off the conveyor belt, and the customer's going to get annoyed if their packages are not already in the sack by the time they get paid. Okay, so there's a very, very short period of time to be able to get this right. Now, some people who've been backers for years have an intuitive sense of this and go, well, if I put that in this bag, and then I'll put this in this bag, and they're good at it, okay? So we're going to do it with math, of course. So all the bins are the same size, all the paper sacks that we're using at the grocery store are the same size. And so one of the techniques is called the first fit technique, which means I basically start with, find the first one that fits. I grab an item and go, does it fit over here? No, yes. Okay, move on. Okay. That works pretty good. So every item you check to see if there's remaining room in one of the bins, one of the sacks. Okay, cool. So here's the algorithm for that. And the algorithm is actually kind of sort of simple. I start up with having all of my my paper sacks set to 0, and then I go through and say, well, if the size fits, if the shoe fits, then put it in there, otherwise move on. So that item goes in, and so the total size gets updated. Now, you might think, okay, well, that makes sense. I'll just, whatever one comes, I'll just put it wherever it belongs, okay? The problem is, this is a horrible algorithm, and the likelihood of you getting a perfect fit, the most efficient, is really low. This technique is about 50% efficient. 50%. If you had 10 minutes to wait, I bet the person doing the bagging probably could reduce the number of bags from 5 down to 4 if you had time. But you don't have time. So you're willing to take 5 bags to the grocery store simply because there's not enough time for the optimum solution. Okay? Good. Okay, we're coming up on the 15-minute mark, so we'll pick this thing up again in just a few.